Hello, welcome to this channel Dr.ARM's Chemistry. Friends, we were discussing the organometallic chemistry, and in that case, today we are going to see the classification of organometallic compounds. Classification of organometallic compounds. Organometallic compounds may be classified on the basis of mainly the type of metal carbon bond. On the basis of metal carbon bond type. So we know that the atoms of various type can come together and form a variety of bonds such as ionic bond, electron deficient bonds, covalent bonds, sigma bonds, pi bonds. These are delta bonds. So variety of bond types are seen when compounds are produced from the variety of combinations between the metals and the non-metals present in the periodic table. The nature of metal carbon bond is determined by the structure of metals and the structure of electronic structure of metals and electronic structure of carbon. So that will define what will be the exact type of bond and the organometallic compound. For this purpose, the properties of metals are very important, in which especially the size of atom and the electronegativity of atom, maybe the atom is metal or non-metal. So if we consider the electronegativity of carbon, this is 2.5 on Pauling scale. So carbon has 2.5 and others are having different. Sometimes there may be like 2.5 or another. So the electronegativity and size of the atom plays very important role in the determining the type of bond. So ionic bonds are formed when the metal is ionic bonds are formed when metal is highly electropositive and the carbon is highly if carbon or the other metal, this ligand atom we will see here, when the ligand is highly electronegative. So this could be identified after calculating the electronegativities of the bonding atoms. Here it is metal and carbon. So we have to find out the electronegativity of metal and electronegativity of carbon, and the difference will give us whether the bond is electron deficient or covalent. If we go to the electrovalent bonds, this is about ionic bond. If the bond is covalent bond, the electron pair electron pair is shared between the bonding atoms. So when the bonding electron pair is shared between the bonding atoms, we know that there is covalent bond formation. In such case, the bond type is two center, two electron bond. Means metal is one center, carbon is another center, and the electron pair is shared between the two bonding atoms. But when the electron deficient covalent bond is formed, electron deficient covalent bond is formed. The bond is means the central metal atom, that is metal atom, is having short of the 8 electron valence shell. Means the outer shell of the metal is not completed because metal has less than half of the valence shell electrons. When the metal has half of the valence shell electrons, then the metal could not complete its octet, and in that case the metal shows electron deficient bonds such as 2 center, 3 electron bonds, 2 center, 3 electron bonds, or multi-center. Means instead of 2 center, it may be 3 center or 4 center. So if we see the cluster compounds, organic metal compounds, cluster compounds, then the centers are more than 2 and the electrons shared are less. Means each covalent bond needs 2 electrons, but in these compounds the number of shared electrons around the metal are short, and that is why they are called electron deficient compound. Now if we see the periodic table, we find that left side of the periodic table there is first A group, second A group, then there is a D block of metals, D block, and after crossing this D block there is a P block. It contains third A group, fourth A group, fifth A group, sixth A group, seventh A group, and eighth A group. Eighth A group here we can see eighth A. So here is metals. From this third A are metals. Third A group contains metals, even though it is the P block element, and these two are S block, which are more electropositive. So most electropositive element is placed in the first A group. Relatively less electropositive means more electronegative element is placed in the second A group. Then this trend is followed in the third A, fourth A, fifth A, sixth A, seventh A, eighth A. This third A group metal is less electropositive than this second A, and in other words we can say this third A metal or element is more electronegative than the second A, means previous element. So as we go in this direction, the electronegativity goes on increasing, and as we go down in the group, the electropositive characters decrease, electropositive characters increase, and electronegativity decrease as we move down the group. On this basis, we can say that the first element, this is not first, but there is hydrogen, but the hydrogen is not a metal, so we are excluding this. The second is lithium, then there is next is beryllium, then there is magnesium, and here we are having boron and aluminium. So these are the more electropositive metals. More electropositive metals. So this is also electropositive. So the three metals are from S block and two metals are from P block. So they make the organometallic compounds which are electron deficient. So therefore electron deficient organometallic compounds. Then if we go to the next elements of this first stage, that is sodium, potassium, rubidium, cesium and francium. So these are, as we move down the route, the electronegativity decreases, or in other words we can say electropositive characters increases. So electropositive characters increase. Similarly, in case of here, we are having calcium, strontium, barium and radium. So these elements are also strongly electropositive. So these metals have shown that they form the metal. This means if we see there calcium, where we will show that these metals. So if we show these metals, so we will show this by this. So these metals are strongly electropositive. So when they form covalent bonds with carbon, means the metal carbon bond, the electronegativity difference is much larger, and in that case they give ionic compounds. Because the electronegativity difference is much larger. And in the complexes, means if we consider these bonds, these metals, then their organometallic compound shows that the metal carbon bond nature is not clearly established. Means it is not clearly shown whether they will form whether purely ionic compounds or covalent compounds. So that is our discussion, especially when we discuss the covalent organometallic compounds of the main group elements. So this is main group elements. And here we are discussing the organometallic compounds of transition metals on large scale. And that is why we have separated the study. Other P block metals, that is elements of these third A, fourth A, that is carbon, silicon, etc. And here the others, that is nitrogen, phosphorus, etc. Seventh A, that is here oxygen. And we are having the sulfur, etc. here, fluorine, chlorine, etc. Then here it is helium, neon, argon, krypton, etc. So these are not giving their organometallic compounds. So especially the P block metals, when combined with metals, means P block elements form covalent compounds which are sigma type. So they give sigma bonds, that is metal carbon bonds, especially, and they are volatile in nature. Then there is D block. So this D block is ranging from third B. Then there is first B, then third B, fourth B, fifth B, sixth B, seventh B, and eighth group. And there are 3 subsections in this group. So this is divided into 3 types. Eighth. So in all there are 10 elements in the row. Elements in the row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 3 rows. And there is again, after this third B, there is first B and second B. Yes. In all there are 10 groups in this block. So these elements are showing that means their electron negativities are suitable to clearly define the nature of this metal carbon bond. So metal carbon bond in this case shows that they can form sigma bonds. That is metal sigma bond. Similarly the metal pi bond, sometimes metal delta bond. So these types of bonds are possible when the metal is from the D block. So complexes will have these 3 types of bonding when the metal is D element, D transition elements. So main group metals form commonly sigma covalent bonds, whereas they will form only sigma. So here the metal carbon bond is of only sigma type. This in these cases. Here these are ionic. So in these cases metal carbon bond is sigma type. And in these cases also. But D block elements have these 3 types of bonding. Therefore, organometallic chemistry of the main elements and transition elements is separated in order to make the study convenient or easy. Chemistry of D block organometallics dominates over the main group elements. The main group elements are also studied, but the quantum of work done on the organometallic compounds is very high, huge in case of D block metal organometallics compared to the main group elements and their organometallic compounds. So this is in short the structure of the nature of metal carbon bond. So for more details, if you want to study, you can refer to the reference book named Principles of Organometallic Compounds. Principles of Organometallic Compounds written by the 4 authors Coates, Green, Powell and Wade. Coates, Powell, Green and Wade. So these are the authors, and this is a very good book. So you can get more information regarding organometallic compounds in this book. Now we will see the bond type, means types of compounds or bond type. So first we will see covalent. Covalent, 2 center, 2 electron bonds, 2 center, 2 electron bonds. These are simple covalent bonds which are ordinarily studied in organic compounds. And there are also covalent compounds in the inorganic compounds also. The covalent bonds in inorganic compounds. The simple metal carbon bond is a single covalent. So this is a single covalent bond. Then ionic characters such as metal carbon bond ionic characters of metal carbon bond depends upon the electronegativity, as we have discussed shortly. The electronegativity depends upon the electronegativity of metal and electronegativity of carbon. So the extent of difference will determine the nature of bond. For example, if we take the organometallic compound such as PH3C minus Na plus, then other compounds like C5H5 minus, that is of twice Mg2 plus. So on the other side, if we see the example of Me3B, this is boron, trimethyl boron, and tetramethylsilane, that is silicon, tetramethyl silicon. So all these compounds are ionic. These are ionic, and the bond is metal carbon, bond is ionic. The bonding is ionic here. Here Na plus and G plus are strongly electropositive than this carbon. So this carbon and this carbon are showing electron rich centers. Predominantly, the covalent bonds are observed in these two cases. So if we see, predominantly the metal carbon bond is covalent. Predominantly covalent. For example, boron carbon bond, as we have shown here, boron carbon, here methyl contains CH3 group, and that carbon of CH3 is bonded to this boron. So here we have taken this boron carbon bond. Then if we find the electronegativity, means why it is this covalent. So that we will discuss here. If we take the electronegativity that is represented by X of carbon minus the electronegativity of boron. So that is given by 2.5 of this carbon minus 2.1 of this boron, and it gives 0.4. The electronegativity is 0.4. So this is less ionic. So greater the difference, the ionic characters are more. Here the difference is less, so ionic characters are less. So this is important factor to be noted here. So as this difference is increasing, the ionic characters are increasing, and as this electronegativity difference decreases, the ionic characters are also decreasing, means covalent characters are increasing. Second example, if we take aluminium carbon bond, so if we calculate the electronegativities of carbon minus electronegativity of aluminium, so this is given by 2.5 as we have seen earlier minus 1.6 of aluminium, so it gives 0.9. So compared to this of boron carbon, this aluminium carbon bond is more covalent. It is more covalent, and it is more ionic in nature. This is less ionic, means more covalent. So here we find that this is monomeric. This bond is calculated in monomeric. It is 0.9. So in this way, so we can compare that this is less ionic, this is more ionic. more ionic. In other words, we can say more less covalent, and this is more covalent. Now, this can be further confirmed on the basis of bond dissociation energy. So we will see here the bond dissociation energies. Which are given in kilocalories per mole. Kilocalories per mole. And simultaneously the boiling points are also given for single metal covalent bonds. So these are given as follows here. The Me2 class is Me2M. Then we are showing here the bond dissociation energy and boiling point. Similarly, Me2, Me3M and its bond dissociation energy and boiling point. Then Me4M star, that is, then the bond dissociation energy and its boiling point. Similarly, we will see the Me3M, then its bond dissociation energy and boiling points. So this is the table which shows the bond dissociation energies as well as boiling points of the compounds. So the examples of this type are Me2B. It has dissociation energy not mentioned here, and the boiling point is 217. Then there is another Me2 Mg. It has no data. Then next is Me2 Zn. It has 42 kilocalories per mole bond dissociation energy and boiling point is 44 degrees centigrade. So this is BP is given in degrees centigrade. Then next example is Me2Cd. It has dissociation energy 33 kilocalories per mole and boiling point 106 degrees centigrade. Then next example is Me2Hg, and it has 29 kilocalories per mole bond dissociation energy and boiling point 93 degrees centigrade. And in this case, the example is Me3B. The dissociation energy is 87 and the boiling point is minus 22 degrees. Then another is Me3Al. The dissociation energy is 66 kilojoules, 126 boiling point. Then Me3 gallium. It has 59 kilocalories per mole bond dissociation energy and 56 degrees centigrade boiling point. Next is Me3 indium ion, 41 kilocalories energy of bond dissociation, 136 degrees centigrade boiling point. And last of this is Me3 tellurium. So it has no data available of bond dissociation energy, but its boiling point is given 147. Then in this case, the data is like this. Me4C, the boiling dissociation energy and bond is 83 and 10 degrees centigrade boiling point. Me4Si, it has dissociation energy 70 and boiling point 27 degrees centigrade. Then Me4Ge, it has 59 and 43. Then Me4Sn, it has 52 and 77 degrees centigrade. Me4Pb, it has 37 kilojoules per mole and 110 degrees centigrade boiling point. Then last table column is Me3N, it has 75 kilojoules and 3 degrees centigrade boiling point. Me3P has 66 kilojoules per mole, 40 degrees centigrade boiling point. Me3S has 55 kilojoules per mole, 52 degrees centigrade boiling point. Me3SB has 52 kilojoules per mole and 79 degrees centigrade. And last is Me3Bi has 34 kilojoules per mole and 110 degrees centigrade boiling point. So this is the data which explains about the strength of the metal carbon bond. So you will find that higher the value of bond dissociation energy, stronger is the bond. So in this case you will find the strength is very high here in Me4C and it is going on less. So the bond becomes weaker and weaker. So here Me3 has 75 and the energy decreases. So everywhere you will find that the Me3B is upper elements shows higher bond dissociation energy and lower boiling points. So these bond dissociation energies gradually are shown to be decreasing and boiling points are increasing. Here also you will find that Me2B is upper element boron has 217 boiling point minus it is higher boiling point and the boiling point is shown to be here varying here. This is Zn. This is Zn. So the values are in this way. Observe to compare the bond strengths of a metal carbon single bond. So we have not taken here the metal carbon bonds of multiple nature, that is pi bonds and delta bonds, etc. We can find that the metal carbon single bond is observed in throughout the periodic table. The bond energies of the metal carbon bond in the methyl derivatives of some main group elements are shown in the form of the plot. So we can show these in graphical form. So if we divide this x-axis on the basis of, as we are putting here the atomic numbers starting from this 10, 20, 30, 40, 50, 60, 70, 80. In this way, so atomic number are shown increasing in this direction, and here we have shown the dissociation energies of MCH3 single bond in kilocalories per mole. So this scale is also shown in the divided into equal 10, 20, 30, 40, 50, 60, 70, it is 80 and 90 and 90. So if we plot the values, we can find that the carbon has value atomic number 6, or you can show here that silicon has the value 10 and 14. Germanium 20 to 30, 60, tin, like this. Then Pb has about 18. Like this. So if we link these, we get this type of trend, and the elements are, this is carbon, silicon, germanium, tin, Pb, this is Pb, and second is nitrogen. Nitrogen, then phosphorus, then arsenic, Sb, here it is, then bismuth, this is bismuth. So if we link these dots, we will get new trend line. And third is zinc. So this will have, these are the elements: nitrogen, phosphorus, arsenic, antimony, and it is zinc, cadmium, and Hg. So this will show trade in metal carbon bond dissociation energy with respect to the increase in atomic numbers. So you will find that in each group you will find that there is decrease in the value of bond dissociation energy. So this explains that within the group, the metal carbon bond energy falls with increase in atomic number. So with increase in atomic number, the bond dissociation energy shows decrease, means the value falls. This behavior is typical of bonds formed between a small first stage group, small first row elements. So these elements are smaller, carbon, nitrogen. So these are smaller elements. So the first is behavior typical of bonds formed between a small first row elements such as carbon and series of metals in a group. Another thing is observed here is that the overlap between the compact, means if we see the smaller atoms like nitrogen, carbon, the 2s and 2p orbitals are merging with each other and they give rise to the hybrid orbitals like sp3, sp2 and sp. So they give sp3, sp2 and sp hybrid orbitals because the atoms are very small and there is no more space, enough space to accommodate the s and p orbital, that is 2s and 2p orbitals. So overlap between the compact 2s and 2p hybrid orbitals of carbon, that is sp3, sp2 and sp, is of greater interest with the valence orbital. While the strength of single metal carbon bond varies very strong is the transition elements, if we see, or the other elements like p block elements like boron. This is not shown here, boron, but if we see the elements like boron, means bond is like boron carbon and platinum carbon. So these bonds are strong. These are strong metal carbon bonds, strong, and comparatively the weaker bonds are found in the compounds like Hg carbon, Pb carbon. So these are weak metal carbon bonds. These are weak metal carbon bonds. So they are generally of a similar order and magnitude to the strengths of single bonds like carbon halogen. So these are comparable to CX, where this X is carbon, this is means X is carbon, nitrogen, oxygen, chlorine, sulfur, etc. So here carbon is this, but if we carbon bonds, carbon nitrogen, carbon oxygen, carbon chlorine, carbon sulfur, etc. So these are also single bonds comparable with these bonds, so which are present in similar organic compounds. So this is about the bond types which are seen here as covalent to central or two electron bonds. Then this is ionic organometallic compounds. Ionic organometallic compounds. So as expected, the organometallic compounds containing the metal ions generally form the ionic bonds because the metals are highly electropositive elements. The formation of ionic bond and compound is especially favored when the hydrocarbon anion is stabilized by complex formation with the suitable metals, whereas the negative charge is delocalized by the organic species, where the structure shows that the organic compound contains some unsaturation or aromatic characters like benzene, etc., or allyl compounds, etc. So they contain pi electrons, and these pi electrons can be easily stabilized. These pi electrons can be used to delocalize the charge on the carbon. So in that case, the ionic compounds are more possible. Means here we can say the anion is stabilized. Means when anion is stabilized by the strong cation, strongly electropositive cation, then it gives ionic compounds. Here if we see the example of cyclopentadiene, that is called in short CP, cyclopentadiene. When this accepts one electron, it gives C5H5 minus anion. So this anion is containing 6 pi electrons. 6 pi electrons. So they can be easily stabilized over the 5 carbon atoms. That is the aromatic system or unsaturation available on the organic part. So such as present in benzene, as we have shown here, the stable anions like halide anions can form salts. Stable anions like halide can form salts with metals. So ionic organometallic compounds are formed when the metal is strongly electropositive and the carbon part, that is part of organic compound, is showing that the negative charge is delocalized all over this, means the electron density is concentrated on the carbon and that charge can be delocalized easily over the aromatic system or unsaturated system. So the example is Mg2 plus C5H5 minus twice. And another example is sodium acetylide, that is Na plus and C minus CH. So this is sodium acetylide. So here the negative charge is concentrated on carbon. Here also the negative charge is concentrated on C5 and it is easily delocalized over the ring because of the unsaturation or presence of pi electrons. So the negative charge is easily stabilized mainly on account of the greater electronegativity of sp relative to the sp3 hybrid orbitals. So here the sp hybrid orbitals are playing very important role relative to the sp3 hybrid orbitals of carbon atom. So we will stop our discussion and we will see the next part in the next lecture. So till then, goodbye, see you next time. Please don't forget to subscribe to this channel and also don't forget to press the like button if you like these contents. So see you next time.